So we'll pick up from the MPI 3 RMA slide. So in the previous discussion we had that MPI 3 is trying to improve the one-sided model and so on, and some new calls have been introduced. So this is just a continuation of that. One call that was missing a lot was that if you did passive synchronization in MPI 2, you could lock only one target at one time. So imagine trying to do that on a very large system, right? You have to do a lock on each target, do your put, get, accumulate, and unlock it. It was very inefficient. So now you have win lock all, which you can lock all targets in a window. And it allows the MPI library to do a collective algorithm, so to speak. And then you have this flush and flush local. What they do is you don't need to wait for the entire window to be over to synchronize. You can call flush, and flush will just say that this operation was completed. All outstanding operations on this window from this processor were completed. So now you can reuse those buffers. So it's like really making it flexible, easy to use, and write languages on top of these interfaces. And WinSync is to just synchronize the public and private windows, and it can be done in a collective call. And another problem which was there in MPI 2, although it was more, mostly like a wording problem, it was that overlapping accesses to the same window. So for example, if you do MPI put on one address and another MPI put on the same address, now so the contents were actually undefined because you don't know which put can get executed first, right? Depending on the resources of the MPI library and so on, because these ordering is not defined by MPI. But the MPI spec said that it is actually erroneous. So what this meant was that especially like the PGAS language developer said that, wait, is the MPI library going to abort if that's the case? Because erroneous means it's going to abort. So they raised a lot of concerns about this, and all of those phrases have been changed from erroneous to undefined, which is most likely, which means that if you have a language on top of MPI and you can guarantee your own synchronization and so on, the MPI will not abort from under you. Okay, so we'll quickly go over the highlights of fault tolerance in MPI 3. So broadly, MPI 2, if there's one process is aborting, everybody dies. MPI 3 is trying to change that. And it's trying to give you the flexibility of detecting when some processes die and just try to sort of carry on. Because there are a large class of applications which can actually deal with that. But they can actually repartition data and continue computing. So in MPI 3, you have 3 states of each rank. One is rank OK, means fine. Rank state failed, which means that this rank has failed. And rank state null, which means that it's not yet recognized as failed. It has failed in between the last 2 operations or something like that. So, so when a rank actually fails and its state has gone to state null, you need to actually verify that that this has failed, and this you can do by calling com validate, and this com validate will recognize all unrecognized failures, and the state info and state set null are just simple calls. So basically, like the point-to-point, what happens in point-to-point is that if you start to do communication with a failed process which is not yet recognized, which means that you have not called validate on that, so the MPI send can return with MPI error rank fail stop, which means that the error, so the destination process has failed sometime in the past. And if you try to communicate with an already recognized failed process, and it will just return by saying that it's the same as communicating to MPI proc null in MPI 2, which is like error send, not error rank fail stop. So what happens with the receives on the receiver side? If you have posted a receive from a particular process which is now recognized as failed, it will return back with an error. But if you post with MPI any source, which means that you are waiting for messages from any source within the communicator, right? So in that case, all of those receives will fail if one process has failed, because the MPI library has no way of intelligently actually, telling you which one has failed and so on. So you'll have to deal with all those receives. So the collective semantics is slightly tricky. What happens if you have a many-way communication and one of them fails? What happens? Do all the processes get a notification that that particular process failed, or is something else possible? So in particular, if you enforce that that rule that all processes have to have a same global status of the collective operation, like succeed or failed, what this does is that it forces the implementation to first check the status of all the ranks and then do the collective, which is in the context of high performance computing, that is prohibitive, and you do not want to do that. So this was relaxed, and we decided that all processes do not have to return the same status. If some have succeeded, they will just return succeeded, and this process will be declared as a fail stop, which means it's an unrecognized failure. But the onus is on the application writer to recognize this failed process before issuing another collective operation. Why do we want to do that? We want to do that because if there is a failed process, you want the MPI library to rebuild the communicator, rebuild the algorithms, rebuild the tree before trying to do the second one. So if any of these processes have failed in a collective with error rank fail stop, which means that some process failed in between this communicator, in between this collective, then you need to validate, and then only you can proceed. So this is sort of like a give and take between the application writer and the MPI library for optimizations. Okay, so now we'll go into the more interesting talk, like part of the talk where we are discussing new features in MVAP 2, which will be upcoming soon. And each one of these bullets is basically one research paper. So the first set of topics deal with collective communication, and the first one of them is using collective offload with the ConnectX-2 adapter. So if you have looked at the ConnectX-2 offload API, it's basically a task list. It's not really like a broadcast offload or all-to-all offload. It's a task list where you can create arbitrary tasks of send, receive operations and wait operations, and you can post that to the network card, and the network card will wait for, will execute these operations and then continue on. So accordingly, the MPI needs to be redesigned to actually deal with this kind of task list offload. So we did a bunch of redesigning and 2 papers here, but over here we are trying to show what's the main benefit of using this network offload. So what is happening in this experiment is that you call I all-to-all, and then you overlap that computation, that part of communication with a dgem call. So every process issues I all-to-all, floating point multiply add, get the peak flops, and then wait for the I all-to-all. What you want to see is that you can effectively hide that communication. There are 2 ways of sort of hiding the communication. One is if you have a host-based method, means that you start a communication, start your computation, break your computation in little bits, And in between the little bits, you issue test calls. Like, you try to make a little progress, right? You do, if your communication is n, you break, and then you can break it up into n by k, and every k slice, you can try to sort of progress the MPI library. And the other approach is complete network offload with asynchronous progress, which is done in MVAPage 2. So over here, we see that if you see the blue line, that's the theoretical peak. So each processor, each node is a Xeon processor with 4 floating point multiply at a floating point units. And we can calculate the theoretical peak very easily. And the gray line is the observed peak. And the red line shows the network offload, where you don't have to break your work into slices and so on. And there you can see that even with small matrix sizes, you can get very good overlap. And compared to the host-based approach, where you'll lose computation because every k slice, you have to poll the network, right? So you'll lose some flops. So this improves your performance a lot. So that was in the context of a micro benchmark. We're just trying to see what is the main benefit. Now we want to do something more interesting. So 3D FFT is a very commonly used application pattern for many scientific applications, for doing turbulence, voice analysis, and all kinds of things. So it's extremely widely used, and it's done within a library called P3D-FFT, which is distributed from San Diego Supercomputer Center. And we actually work with those people there. So typically what will happen is that every application will have multiple variables on which they're trying to do FFTs, right? UVW components. And each of these components is a 3D data set. So this FFT basically boils down to an all-to-all, which is doing a local FFT on your local stride, flipping that slide over, and doing the FFT on the other dimension. So like naturally, all-to-all is the bottleneck, because your local FFTs are done by actually using FFTW and very advanced local libraries. So your all-to-all becomes a bottleneck. So there are two ways of improving it. Either you make your all-to-all go that much faster, or you overlap the all-to-alls with computation. So like making all-to-all faster is an existing problem which has been tackled by many researchers, and we have optimized it almost to the last 5–10% of performance. So we can't go much there. So we want to see, can we combine the network offload and the all-to-all overlap to see real benefits. So what we have done is, you have 3 variables, say like UVW from a scientific application. While you're doing the flip of the matrix on one variable, say U, you can start doing the local FFT on V. So now these two things are going in parallel together. And you can see that now you have improved the performance with the offload. So the blue line is the blocking, which is obviously the worst. And this green line is basically like a host-based version, where you start the I all-to-all, and then you probe in between, where you can gain a little bit of overlap, right? Because you're trying to probe a little. But you also waste CPU because you are having to break the whole thing into 2. And it's, again, a very key observation is that if you break like a nicely divided problem into multiple chunks, it actually reduces the efficiency of the serial library. So like your BLAST library is optimized for large block sizes. So if you have broken that into small block sizes, now your BLAST library is also not operating at your full efficiency. So we think that this is exactly where things like network offload make a lot of sense for very demanding applications, really. And we have a publication here, which is upcoming. Then we have topology-aware collectives. Now, this is a real problem on on our one of our primary users, which is that Ranger, you have all these racks with all these compute nodes. And now you have different levels of switch hierarchy, and depending upon the communication, some of these switches can become a bottleneck. So we need to solve this. And if you look at these jobs can be sort of scattered all over these racks. Now you may ask is that, can't we have a much more intelligent scheduler which will put all these jobs in the same rack? But it's not so easy to come up with that scheduler, because scheduling is an NP-hard problem. And these jobs can arrive at different times, complete at different times. So even though you start off with a nice block-based allocation, over time your jobs will fragment. And there have been like 15, 20 years of research in the scheduling community, but still this is the state of the art. So instead of fighting that battle, can we have a better collective algorithm within the MPI library which can deal with this kind of problem? So just quickly showing a paper presentation from IPDPS last year. Here we're showing that like a topology-aware algorithm can have significant improvements, like 50% in the case of gather, 20% in the case of scatter. And the basic idea behind these algorithms is that you have, for every rack, you have a leader. So you can overlap inter-rack communication with intra-rack communication. So you can sort of like optimize it. Instead of all the members from one rack hitting the congested link at the same time, you can sort of like have a schedule. Like if within this rack I have 1,000 processes, I will at the same time I will only allow 10 processes to go on the inter-rack link, because that's the bottleneck. Because if you just allow a lot of these things to go on the same link, that they're just going to get more congested. So now we'll take a look at power-aware collective algorithms. So the default mode is that you call your collective algorithm, maybe blocking, and you just run each core at existing frequency and just keep doing it, and don't do any throttling. So there's no power savings there. You can do a little bit more intelligent, where you can, as soon as you're within the collective, you slow down your cores by using DVFS. You can save a little bit of power, but now your cores are also going slower, which means that they are accessing the network a little bit slower. And in the case of computation-based collectives like all-reduce, you can hurt performance. But if you take a even more intelligent approach and know that your network links are congested anyway, and if you can tie that with the schedule of the collective operation, you know exactly which processes are going to access the congested link. So if you know that I have an all-to-all, and from this rack, at this point of time, k number of processes are going on the congested link, the other processors can be completely turned off to almost very deep sleep levels, because it's not going to get over soon. So we can combine these two techniques with the knowledge of the collective pattern to get a lot of efficiency. So over here we are seeing that, I think this is with all-to-all. And we see the latency of the default versus the proposed. We say that like the proposed, even with power savings, it only does 5% worse in terms of pure latency. Like you call all-to-all, you do your power-aware stuff, and then you sort of like measure the time. It's only 5% more, but you save 32% power. And then this is like, from this data, we actually used a watt meter to actually measure this power. This is not estimated. This is actually measured. And then from this measurement, we have developed like a model for this stuff. And we increase the system size, and for all-to-all, we increase it, and then we see that for large systems also we can see this gain. And it is intuitive to understand why you would see this gain. So that was at the MPI all-to-all level, which is sort of like a micro benchmark. And now we want to see what happens at the application level. So this application, CPMD, is very all-to-all intensive. And here we see that the estimated power savings are about 8%, and the performance degradation is not as much as the power savings. And in fact, you can push this number even further up, because if you just want to fit within the power budget, right? Like sometimes applications don't need to run the fastest, but they need to fit within the power budget. You can actually make that even more aggressive, and we have some work which is going on to, see exactly how far you can push it down. Any questions? Okay. Next slide. So now we look at something which is most interesting, and I think it was actually discussed over the last 2 days, and we'll take a quick quick recap of GPU Direct, although it was discussed by Sadaf and Tim yesterday. So what is GPU Direct? It allows both the InfiniBand HCA and the GPU to share the same system memory. So if you share the same system memory, you don't have to copy GPU buffers and CPU buffers. You can use the same memory to actually come in. So MPI 2 supports both GPU Direct V1 and V2. And these numbers are actually with V1. What we have done here is made a bunch of optimizations with GPU Direct, and you can see that we can see a big difference here with up to 12%. And even without GPU Direct, we have made a lot of improvement in the 1.6 release. And here you can see this performance, and that's the dip, Sadaf, you were mentioning, without GPU Direct. And then even with collectives, you can see a lot of improvement with up to 25% in the case of in the case of all gather, and some in the case of all reduce, all to all, and so on. So GPU Direct V1 is actually helping a lot. Now, what is new in CUDA 4.0, and what is new in V2, which is of more interest? So just to have a recap from the NVIDIA presentation yesterday, is that it has unified virtual addressing, which means that all your GPUs and your CPUs can see the same memory address space. This is very interesting because this now enables the MPI library to know that given a buffer, where does it sit? Is it in the GPU or is it in the CPU? So actually we have a research prototype of MPI 2 which can actually take this information and convert this into much improved performance. So like the current state of the art is that if you want to transfer data from one GPU to another remote GPU, say as a part of all-to-all or as a part of MPI Send and so on, what do you need to do? You need to CUDA memcopy that buffer from GPU to CPU, then call MPI Send to actually send it, and then on the remote side, you actually need to CUDA memcopy it back. So there is a lot of efficiency which is lost here, and we want to improve that. So over here, what we have done is, because MPI 2 can now see that whether this buffer is in the CPU or the GPU, you can just call MPI Send directly from that GPU buffer. You no longer need to stage it in your host memory. If you call MPI Send and MPI sees that where this buffer is in GPU, it can perform very efficient pipelining to the system memory and actually pipeline that memcopy with another InfiniBand Send. So if you have two PCI Express buses and the GPU is on the 16x bus, and your InfiniBand is on the 8x bus, you can use all these buses at the same time. You no longer have to wait until one is over and then start the other. So we took several such examples. Of course, the green line is your default implementation, which is, your red line is your default implementation, which is simply CUDA memcopy and MPI Send. This is supported by GPI Direct v1, and which is normally done by applications. So the application writer can actually become a little bit more intelligent and say that, look, I know that these two things can be sort of overlapped. What I can do is I can use CUDA memcopy async. Like I can have an asynchronous memcopy and then use isend. So I'm trying to do the pipelining myself, right? But there, what happens is that now not only does the programmer have to spend more effort, what happens when the same program is now executing on IB FDR cluster? So all of a sudden, all these parameters have changed, and the programmer doesn't know, where the performance is being lost. So it is better to actually let a system-dependent library deal with this kind of stuff. And there's another optimization which we can do. If the programmer is trying to break this down at the MPI level, for every MPI transaction, there has to be a round trip within the network, because on the remote side, you need to know where to land the buffer into. If you let MPI deal with this, this sort of pipeline transfer, then MPI can do this synchronization only once. It can do it only once, and then after that, it's just pipeline RDMA writes. So it's a lot faster. So if you compare this red line versus the green line, which is the best we can do, you can see it's almost 45% better. And of course, this is going to show up in applications. And over the last 2 days, we saw that several applications have been using GPU Direct and actually getting good performance improvement. Now, if you add these two things together, then you'll get much more improvement. So this will be presented at ISC.
Yeah. What is the best MPI level?
Oh, yeah, I forgot to mention that. So the question is, what is this magenta line? I don't know if it's visible. What is this magenta line? So this magenta line is if you just use MPI send from point A to point B from your host, from your host memories. So this is just like if you're just doing that, and like with your GPU Direct, you can actually you don't have to wait. What did I say? No, I think my description is wrong. I should talk to you later. I need to read the paper. So I think the best MPI level latency was further fine-tuning the pipeline sizes. Yeah. All right. So any more questions on that? Yeah.
If I ask like a little bit
Yeah, so this is just a research prototype for now, and I mean, we are going to try to make it available, and we are in discussions right now, so we can answer that question later for you.
Okay.
But as such, it should work with the applications as well. Okay, so the third topic which we are going to discuss within MVAPage 2 is the support for PGAS. So like UPC and PGAS are gaining a bunch of interest, and exascale computing has actually set out a roadmap for doing the programming models, and everybody knows that MPI is going to be there for doing inter-node communication. It's not so clear what's going to be there inside the node. It could be OpenMP, or maybe it could be like PGAS. And that's the phrase which is being used as MPI plus X, which is required for doing exascale computing. So if you take the current approach of PGAS, then you basically have to re-implement all of your numerical libraries, everything inside PGAS, which is very, very hard to do because there's like hundreds of man years of effort which has gone into these libraries. They simply cannot be reinvented. So we want to use all of our InfiniBand expertise to actually leverage that for PGAS. And what it should allow like an application writer to do is they should be able to tinker with with the application and just optimize little parts of it to use UPC, as opposed to converting the whole thing into UPC. So they can make a little bit of the application inside UPC, and then you can just reuse all the other rest of it in MPI. For example, MPI collectives and so on. So we really need a unified runtime here. So why do we actually need a unified runtime if we just want to use both things together? So here's one example of what happens when you mix a one-sided programming model with a two-sided programming model. Here, what this is doing is like this P0 is trying to do a memory get from P1. So it has sent the memory get request, and then it enters the MPI barrier. And then P1 has also entered MPI barrier. So now P0 is actually waiting on the memget request because it's a blocking request and it's spinning within the UPC runtime. But P1 is spinning within the MPI runtime. So like neither of these messages can be discovered, and this is a deadlock. So currently, what UPC people ask application developers to do is before you call MPI barrier, you must call UPC barrier here. But that is a really bad performance because it means that you have to phase your UPC operations and then go into MPI mode and then phase it back. So it kills overlap, it kills all your performance. So the only way to solve that is actually make these messages discoverable by each of these runtimes. So over here we have seen that if you have MPI, then you have the MPI runtimes, buffers, queue, and so on. And then you have the UPC compiler, you have the GasNet interface, and then you have GasNet runtime, and so on. But finally, they're talking with the same network interface. So we have a unified MVAPage to GasNet runtime. Everything is completely unified, and both of these, like this UPC compiler, GasNet, MPI can just run on top of the same interface. We call this library our like unified communication runtime, and this runtime provides active message APIs, which can send short messages without arguments, where we encode the zeros inside the header handler, so to speak, so we can save on the network request. We can have medium-sized active messages, large active messages, so on. And we have extended the GasNet interface for efficient RMA, for doing inline puts, put, bulk, and so on, get with RDMA read, and so on. So if you take a look at this, like this unified implementation of UPC and MPI, both MPI, and in this example, like both the MPI message and the UPC message from this node is trying to go to this node. So, and then we have the same communication connection with the same buffers and so on. The only difference is internally we know if this message is an MPI message or a UPC message. If this is an MPI message, when this message is received on the remote side, it can be added to the MPI message queue. But if this is a like an active message, which was issued by UPC, it can be actually given off to the active message table and assigned its own active message handler. So these buffers are exactly the same. So underlying network transfer is the same as sending 2 MPI messages. This is also a little bit of a dense slide. So what happens is, like, currently also you can run a UPC application on top of MPI. So over here, what we are trying to show is that what are the different modes in which you can already run a UPC or MPI or a hybrid application. If you have a pure MPI application, of course you can use MPI2 optimized runtime and so on. And then if you have a pure UPC application, then you can go through the GasNet runtime. If you have a pure UPC or UPC MPI application, what you can do is you can use a GasNet MPI runtime, where GasNet will map to MPI calls. And then you can sit that on top of MPI2 or any MPI2, and this will work. But you will lose efficiency here because the MPI interface itself is not optimized for GasNet. It doesn't have active messages. And actually, GasNet depends on active messages. Over here, and this is our contribution, is that with the UCR, you can interface that with GasNet, and that actually sits on top of MPI2, where all this connection management, flow control, routing, all these things are there inside this optimized runtime, and they can be used for your hybrid application. So this enables a new flow path, so to speak. So this slide is just trying to show that if you use the GasNet MPI runtime, you pay a significant latency hit. But if you use either the native GasNet IB verbs, or you use our UCR conduit, you get the same latency. So you don't lose anything by making it actually hybrid. And then you also gain all these memory scalability enhancements, which DK talked about yesterday, with our UCR runtime, and you don't have to really worry about re-implementing all this for UPC. And as I said, this main cause this number is sort of higher is because because there's a mismatch between the MPI, API, and the GasNet requirements. And this is a slide from like a more recent work. Here, what we have done is, like, the UPC runtime on a multi-core node can be implemented in 2 ways. One way is that all the UPC threads have been assigned pthreads within the node. Another way is that all the UPC threads can be assigned processes within the node. So why do you want to assign pthreads? Is because if you have any kind of work stealing going on, right? If you're trying to run Silk and UPC, or if you're trying to do any kind of other work stealing, you want a multi-threaded runtime. And if you run GasNet in that multi-threaded mode, you see this horrible latency. Here we are actually using 2 Intel Westmere nodes with ConnectX QDR, and they have 8 cores each. You see this horrible gray latency. And if you use our runtime, where what we are doing is, you'll get this red line. We have each thread is assigned an endpoint by themselves, so it's a completely lock-free design. And by using this, you can get the same latency as your your processes, where your UPC thread is the same as the OS process. But now you cannot use work stealing or anything like that. So this multi-thread latency can be brought down by 80%, from 15 to almost 2. And for 1K messages, your bandwidth can be raised from 72 to about 200 megabytes per second. Another slide which actually shows the application level evaluation of this UPC and MPI interoperability Here we are trying to execute UPC versions of the NAS benchmarks on these various interfaces, and here we can see that this GasNet UCR, the blue line, is what you should be looking at. So the blue line always performs equal or better than the other lines. So this will leverage all the MVAPage to work for UPC without having to redo anything. And finally, this is an actual hybrid NAS FT, where the UPC version of the NAS FT has been modified to call MPI all-to-all, as opposed to UPC all-to-all. And this purple line is the hybrid line, where it's actually a UPC program which is trying to use MPI internally. And then you can see this great performance improvement, 34 performance for C with 128 processes. So there are good use cases for such hybrid programs, because many times the UPC collectors will not be the same optimizations as the MPI collectors and so on. So finally, we'll mention our future plans and conclude. So MVAPage 2 is planning to go to exascale. We want to have scalability from like million to billion processors with very, very low memory footprint, and we're working towards that. We also want to support hybrid programming, where you mix and match programming models. We don't want to give you any sort of restrictions that you have to use only one programming model, and UCR is our approach towards that. We want to balance intranode and internode communications, because multi-core systems have a lot of cores, and I think Dell announced a 96-core system. Next year it's going to be even more. And then we want to focus on the scalable collective communication, because that's the key for actually scaling these communications across many nodes. We want to support multi-threading, fault tolerance, resiliency. DK has presented some slides yesterday about fault tolerance. We didn't get time to go in that today, but we have several works coming up there. And then finally, we want to have QoS support for I/O. We do not want storage communication to be interfering with MPI communication, or having better MPI communication with our VL scheme, which he presented yesterday. And of course, we are going to support MPI 3 pretty soon, as soon as it's possible. So. Finally, we want to conclude this series of 3 talks. Thanks for Brian and Gillard for inviting us to give these talks. We have presented the challenges for designing exascale systems. We gave a good overview of whatever the MPI 3 features are, what are the new shiny things, how we, in particular, are trying to address some of these challenges with large InfiniBand clusters, and we presented our roadmap. With that, I would like to acknowledge all the funding given by all these lovely organizations, and our equipment, which was donated by many of these organizations. And DK also likes to acknowledge all of our students and the people who have been working on this project for almost last 8 years. And it's really just a joint effort. We are always in sync about doing the next thing. And with that, I would like to conclude our talk and point you to our website for any more information about papers and so on, and feel free to contact us.